Okay, so today we are going to continue our conversation about linear ODEs and homogeneous equations in specific. You may recall we said a linear ODE looks exactly like this, and this is called the Forcian function. And all these functions in front of the y's are functions of the independent variable x or t. And we said that if the Forcian term is 0, or if y equals 0 is a solution, then the ODE becomes homogeneous. Okay? And why was that important? It was important because we said if you have a homogeneous equation and let's say y1 and y2 are solutions, then a linear combination of both will also be a solution if you have a homogeneous equation. It would actually will work as well for non-homogeneous, but we haven't addressed that problem yet. Okay, so today I'm going to work out some examples and share with you a couple of really cool things. I am gonna entertain the idea of second order as well, because really whatever works here as well. And I deliberately write a subscript 2 to reflect the double prime and a1 to reflect the prime, just so you remember how to write it. You don't have to write this. You could call it a0x, a1x, a2x, or f of x, g of x, h of x. I don't care. I just like to use notation that will help me remember how to write things down. So I'm going to work out 3 examples, and the first one is basically a homogeneous ODE, and so as the second one. I'm deliberately killing this piece here and making a subscript 2 of x and a0 of x to be 1, right? Just to keep it simple. So, and the reason I simplified it is because I want to take advantage of this very quickly, okay? So, what this says, this is a second order linear homogeneous ODE, okay? What it says is the second derivative of some function is the negative the function. Remember that y double prime is negative y, okay? We can probably guess that sine x or sine t would work because if you differentiate sine function twice, you're going to get exactly the opposites of the original function, right? So we know this is a solution. Again, if you add this to this, you get 0. And that is exactly what this says. Similarly, I can pick another solution, the cosine, right? Because if you differentiate the cosine function twice, y double prime of 2 negative cosine t. Once again, if you add this to that, you're going to get 0. Therefore, this is a solution. And in conclusion, C1 sine t plus C2 cosine t is a solution. Why? Because this was a solution and this was a solution. And therefore, a linear combination of 2 solutions is a solution. Okay? We're going to do this the same way, but now this time the second derivative is the original function. Well, everybody can guess e of t, e to the power of t. Because e to the power of t, if you differentiate it twice, you get e to the power of t, and if you subtract the second derivative from the original function, you get 0. You can also probably guess, so this is a solution. The other solution is e to the negative t. Again, if I differentiate it twice, and I subtract this one from this one, I get 0. So this is also a solution. Oops. Y equals e to the negative t. So this is a solution, solution, solution. Therefore, c1 e to the t plus c2 e to the negative t is a solution. Okay? So now I'm going to make it just a bit harder, and I stick in a 4 here or a 9 or whatever I want to stick in. I decided on a 4. Let me change it to 9 for fun. Okay? Now some of you might be able to guess it because you have to differentiate twice. So most of you will probably guess e to the 3t. And I chose 3 for the following reason. We differentiate once, and then we're going to differentiate the second time, and then 9 pops up. So clearly this is a solution. And y2, you can probably guess this one as well, because the negative 3 drops, and then the negative drops again, the negative 3 drops again, and you get a 9. So these are my two solutions, and therefore c1 e to the 3t plus c2 e to the negative 3t is a solution. Now some of you might say, well, I couldn't guess this. How the heck am I supposed to guess this or that one? So that's what I want to address next very quickly. We know it's going to be exponential. So the question is, what kind of an exponential would I get? Well, we're just going to guess e to the kt, okay? So that means y1 prime is k e to the kt, and y double prime is k squared e to the kt. There is a t here. So now I'm going to plug them in. I'm going to plug that in here. Okay, so y double prime is k e to the kt minus 9 e to the kt. Here's what I did. I took y double prime, here it is, minus 9, the y, what we think the solution is going to get. And for it to be a solution, it has to satisfy the equation. So I have to write 0. So we're going to factor out e to the kt. And I made a mistake here. This is supposed to be k squared, right? K squared. Because when you drop k again, you get k squared. So this is a k squared. Eventually, you'll catch yourself, and you'll see why. So when I factor it, I get k squared minus 9 equals 0. So we know that e to the kt is a positive quantity, so it cannot be 0. So that means k squared minus 9 equals 0, which means k is 3 or negative 3. And then you can go back here and plug them in. That's how you would get it if you really couldn't guess initially. So that's why I did this problem, okay? Now, of course, I made a mistake here. So I would have gotten k minus 9 equals 0, which means k equals 9, which means the solution is e to the 90, and e to the 90 would never work, okay? So now I'm going to work a general case. I'm going to take a homogeneous linear ODE, second order. But this time, I'm going to pick all the functions in front of the dependent variables to be just constants. Because if you understand this, then you can get all the ones we did, including this one. You can get all of them for free. So the general solution, one of the solutions is going to be e to the kt, just like we did before. And I'm going to go back to the first one, which had a sinusoidal, has a sine and cosine. I'll deal with that later. So we're going to plug in the same thing. So y1 is that, and therefore we know that y1 prime is that, and y double prime of 1 is k squared this time. I didn't forget. It's k squared. So we're going to plug them in. We're going to get a k squared e to the kt plus b k e to the kt plus c e to the kt equals 0. Factor out a to the kt again. I get a k squared plus b k plus c equals 0, which means a k squared plus b k plus c equals 0, because e to the kt cannot be 0. Okay? So this looks to me like a quadratic equation, isn't it? Okay? And you can use the quadratic formula or factor, but the solutions, we call them the roots, right, will let me know what to put in here. Remember, your k is your x. A, b, and c are constants. Your k is your variable in just this case, okay? So basically, the solution to this equation, I'll put it in blue this time. This equation is called the characteristic equation, or characteristic polynomial. Okay? So basically, every time I see a homogeneous equation like this one, I can literally jump to here and just solve this quadratic equation. And whatever the solutions you get for k will be the corresponding values. So let's say you get k equals, I'm just making up stories. Let's say you get k equals 3 and k equals 4, or r1, r2, right? These are the roots. So my solutions will be e to the 3t and e to the 4t. That's all there is to it, okay? So the moment you get a homogeneous ODE in this form, you can immediately jump to here and just solve the quadratic equation out of the characteristic equation, and you are done. So now the question becomes, what happens to the first one? I'll remind you. The very first one we did, not the second, but the first one, we guessed the sine and cosine function. We did not guess exponential functions. Well, how does that equate with what we got all the time? We got the exponential functions. So let me use the characteristic equation here, pretending we couldn't guess this. Let's say we couldn't guess this. And I'm going to just take full advantage of this concept to see what we get, okay? It's nice to explore. So we are going to guess. We can jump to the characteristic equation immediately, or which is going to give me k squared plus 1 equals 0, right? But let's say you didn't guess that. You can assume, again, an exponential 1. The second derivative will be k squared. Oh, my goodness. I don't know what's happened. K squared e to the kt plus e to the kt equals 0. You factor out e to the kt and you get this. Okay? So I jumped from here to here directly. That's what I was trying to do here. Okay? So that means, of course, that means k squared plus 1 equals 0. The solutions will give me plus or minus I. And therefore, my two solutions are e to the it and e to the negative it. And of course, we could use the superposition principle, and we can get this solution if we care. C1 e to the it plus C2 e to the negative it. Okay? The question is, how come we got this one, but in here we got these? So we need to reconcile that piece. So I'm going to take you back to a little bit of calculus. Okay? You may remember from Taylor expansion that e to the t, let me write e to the x so I don't confuse anyone. It's the sum of x to the n over n factorial. N goes from 0 to infinity. I hope you remember that from Taylor expansion. I keep writing x. Okay, n equals 0 to infinity, which is basically x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x squared over 2 factorial, and so on and so forth. I'm going to write it nicely. 1 plus x and also, you learned that the Taylor expansion for cosine of x was basically the terms in here that happen to be even functions, right? Because the cosine function is an even function. So you get 1. 1 is even. If you have y equals 1, then f of negative x is also 1, right? So the function 1 is even, so that's going to have to stay with the cosine function. So we have 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial, dot, dot, dot. And the sine function is odd function, so it only includes the terms that are actually by themselves odd functions. So for example, f of x equals x cubed is an odd function because f of negative x is this, which is this, which is this. So it will never include x squared and x to the 4th. It will only include the odd powers. Okay? And what you also did was e to the ix or it or I theta equals cosine theta plus I sine theta. Okay? This is called Euler's formula. And of course, e to the negative I theta is the same thing as e to the I negative theta, which is cosine of negative theta plus I sine negative theta, which is cosine of theta minus I sine theta. I could have written this directly, but somebody's going to question why did this minus go here? So that's why I did it. And just as a side note, when theta is pi, it turned out to be a beautiful equation. You get cosine of pi plus I sine pi. And I love this equation, especially if you write it this way, e to the I pi. I'm going to move this negative 1 to the side, and this is 0. So we're going to get plus 1 equals 0. This is beautiful. It is the simplest equation I can think of that involves the most powerful 5 numbers in mathematics: 0, 1, pi, e, and I. 0, 1, e, I, pi. Okay? I don't like it written this way because you don't see 0. In any case, that is a side conversation. I'm going to erase it. Okay? I don't need it. Now, so we're going to go back. So let's see where we are right now. We learned that y1 equals EIT was a solution. We also learned that y2 is e to the negative it. That was a solution, and it is here, in case you forgot. Okay? And we learned last time that the principle of superposition applies, which means any combination of these two should also give me a solution. And I'm going to choose this combination: half of EIT plus half e to the negative it. I just pulled the half out, okay? So I have the right to say half EIT, half y1 plus half y2. Now, we just learned that e to the it is cosine t plus I sine t. And e to the negative it equals cosine t minus I sine t. We just proved it, okay? So if you add them up, you're going to get twice cosine t, because this piece cancels. And if you divide and if you multiply both sides by half, so half EIT plus e to the negative it, you should get cosine t. Isn't that beautiful? Which means this solution we got at the very start makes sense. Okay, so there is absolutely no contradiction between getting these two solutions and getting these two solutions. All I did is I took these two solutions and I applied the principle of superposition to get the cosine t. I could do the same thing to get the sine t, but this time I am going to take C1 to be half I and C2 to be negative e to the it. Let me slow down here. Let me slow down, okay? So I'm going to pick C1 to be half I, okay? And C2 to be negative half I, or negative 1 over 2 i's. And what I'm going to do, I'm going to add them again. I could have picked the same C called 1 over 2i, and I will subtract them, but this time I'm going to add them up. So if I add them up, I get half 2i cosine t plus I sine t minus 1 over 2i cosine t minus I sine t. And if you do the math, you will get sine t, which is what we got in here. Okay, so you can maneuver both. So that should conclude this particular conversation. But since I mentioned this, I want to take a full advantage and share with you something really cool. So that has nothing to do with our course now, okay? So we know that e to the I theta is cosine theta plus I sine theta. And by the way, e to any complex number is going to have to be e to the a cosine b plus I sine b, right? The reason is this is e to the a times e to the ib, right? Which is e to the a times this. Well, this is exactly this, just b is your theta, right? So you get that. We can also write it this way. For simplicity, e to the power of a cis b. You remember cis b is cosine b plus I sine b. All right, so let me show you a trick. And then I'll end. Gets excited about this stuff. All right, so what is e to the 2t I? Well, that's going to have to be, what do you think it is? It's going to be cosine 2t plus I sine 2t. Isn't that true? This is your theta, right? Now, I can write 2ti like this. ti plus ti. And I'm going to use the magic of Algebra 1 to call it e to the ti times e to the ti. When you multiply two powers, you add the exponents, right? Now, this happens to be cosine t plus I sine t. And this happens to be the same thing, cosine t plus I sine t. I could have just squared it, okay? So if we square that, what do we get? We get, actually, it's much better just to square it. It's a little cleaner. So basically, this is e to the it squared, right? So you square a binomial, you square the top, the first piece, plus the square of the second piece, plus twice the product. Now, so this is, I'm almost done. So this is cosine squared t minus sine squared t. And then you have 2 cosine t sine t I. And this is beautiful. What it tells me is something you learned a long time ago. Sine of 2t is twice sine t cosine t. That's one of the, I'll put it in red, one of the formulas we learned in basic pre-calc course. You also learned that cosine 2t, which can be written in 3 ways, one of which was cosine squared t minus sine squared t. I hope you remember this from pre-calc. Well, it just pops up. Cosine 2t is cosine squared t minus sine squared t, and sine 2t is 2 sine t cosine t. I thought you might appreciate that. So that should end our conversation. Once again, thank you for listening, and I will talk to you next time.